Hello, everybody. This is our BE 453 Rehabilitation Engineering Final. My name is Kamal, and I'm recording with Victoria, Donnell, Jason, and Aron. So let's talk about abnormal gait rehabilitation. So possible causes of foot drop are multiple sclerosis, perennial nerve injury, but we're actually focusing on stroke. A lot of people have problems with lifting their feet while walking once they have a stroke. And once they get rehabilitated for it, it actually takes a lot of time during their appointments to set up the equipment just so that they can get the rehabilitation. They often spend a huge chunk of the time just setting up, and then they often lose out on a ton of therapy time, causing a longer rehabilitation time, which sucks for them. So we intend to automate the nerve calibration for the foot drop devices so that post-stroke patients have better rehabilitation experiences. We want to increase the ease of use. We want to increase the rehabilitation and therapy time by decreasing that setup time. And then we also want to decrease the total amount of time a therapy is required for the patient. So to do this, we're actually creating a device that is a knee unit and a heel sensor so that we can help foot drop patients get rehabilitated faster.
So when designing this device, we separated it into 5 different phases. And phase 1, we talked about operation designs. So the first thing we did was to determine what our device wanted to do. So the operational requirements, and we ranked it from uh, rank of importance, 1 being the most important and 4 being the least. So for the first one, we wanted the device to be able to lift the front of the foot when walking or moving. So since the purpose of this device is to help users with foot drop, we wanted to lift the foot instead of having their feet drag when they walk. Second, we wanted to locate the person's peroneal nerve. So in order to lift the person's foot off the floor, we need to find the correct nerves. So like we can send proper electrical stimulation for the foot to lift up. And for 3, we wanted to indicate low battery since it allows the patient to know when the device needs to be charged. So the patient doesn't suddenly like fall when like crossing a street, for example. And for 4, we want the device to be able to be easily stored since like it's going to be constantly on the person's leg. You want it to be portable, compact, and like they can put it somewhere easily since the device would be expensive. So for functional requirements, here's a list of them. The first one we talked about is to find an automated nerves finding system because the most important thing is to find the proper nerves so the patient can focus on rehabilitating, like walking during the therapy sessions. 2 is a rechargeable battery since the battery powers the device and you wouldn't want the patient to constantly have to switch batteries since that would be really inconvenient. And 3rd, we wanted to determine when the electrical impulses needed to be sent again to the foot, since to walk, you constantly lift your foot up. So we use a heel pressure sensor for that. Uh, so here's a list of performance requirements that we wanted our device to have. The first thing, most important thing was the processing time because current devices like we want it to have a quick and efficient processing time so there's no delay, because if there's a delay, it might cause the patient to fall and trip while walking. We want a long battery life since the device may need to be used for long periods of time depending on what the patient is doing. And constantly recharging device would be a hindrance to like everyone in general, I guess. And uh, 3rd, we wanted to decrease the time it required to locate the nerves so patients could have more time to like walk and they wouldn't have to prepare that much when they wanted to go somewhere. And for 5 and 6, their metrics, average steps, and how long it takes for a patient to walk a certain amount. They're metrics to measure how the patient is improving throughout each session. So wait, I'll go back. So an overall system review, we want a lightweight material and durable. We want a lightweight material and wait, we want the device to be made out of lightweight material and be durable. That also has buttons, so it's easy to configure. We want electrodes to attach to the human leg, power to provide electricity to the device. Uh, We want a heel pressure sensor to determine when the foot is on the ground, and software to determine the mode to use and interpret the data from the heel sensor and make decisions like when to send the electrical impulses. And yeah, next slide. So this is our functional flow. Uh, like how the first thing you would need to do when using it is to calibrate the knee and heel unit, and then after placing it in the proper areas, you would choose the operating mode and adjust the stimulation intensity, since each patient would require different intensity of electrical impulses. And then the patient will walk, and then you would recharge the device after the patient is done using it.
Phase 2 of the project is the mechanical phase. In this phase, we'll start with the requirements and criteria. The requirements for the project include a calibration system where the system can find the correct nerve to stimulate without guessing and checking from the user. Touchscreen user interface is needed, heel pressure triggered aid when walking, and a way to alert the user of low battery level while the device is in use. The criteria for the selected components are the breathable materials must be used since the patient has to keep the device on their legs for extended periods. The materials must be durable and lightweight since the user needs to feel comfortable while wearing the device. And long battery life must be kept so that the user can use the device without feeling anxious. Critical components for the system include a touchscreen and the heel pressure sensor and the microcontrollers. The touchscreen will allow the user to interact with the device and initiate the calibration sequence. There is also a pressure sensor which can be used to see if the person has their foot on the ground or in the air while walking. When the heel is on the ground, pressure will be recorded and no electrical stimulation will be applied to the leg of the patient. Once the heel is lifted and the pressure is no longer recorded, the system will know that there is a need for nerve stimulation. No breakout board is required to connect the sensor to the microcontroller so space is saved. Next are the two Arduino boards that control and make sure everything is running smoothly. On the left, there is the Adafruit Metro M0, which is a larger MCU for the knee unit. Both of these have the exact number of pinouts that they need, and the compatible storage also works for both systems. And they also have Bluetooth built into both of them so that they can talk to each other. Now, the smaller one on the right is the Metro Mini, which has less processing power and fewer pinouts because they just aren't needed for the heel sensor. Some minor components of the system include the on-off switch, LED lights, and a speaker to notify if there is a low battery for the device, an accelerometer to measure the leg speed for our control problem, batteries and battery holders to power the device, and breakout boards to connect some of the components to the Arduino. The previously mentioned components were all parts that could be purchased and will come ready for use. A custom component that must be fabricated by us is the matrix electrode we will be using to stimulate the legs and the the nerves in the leg. There are 30 electrodes in the matrix, and how the calibration works is that once the calibration sequence is initiated, electrode 1 will be stimulated, and then the system will check if the pressure sensor feels any twitches from the foot. If pressure is felt from a twitch, then the electrode will be used to stimulate the leg during use. If pressure is not felt because it's not the correct electrode, the process will be repeated with the next electrode. This automated process cuts down on this setup time during the rehabilitation therapy appointment, which is what makes our device unique. Lastly, we will have the two actual components of the system, the knee unit and the heel unit. The housing will be made custom for both of them. A polycarbonate housing will be used for the electrical components, and it was chosen since it's commonly used in many electrical situations where you don't want your components to be exposed to outside elements. It is also lightweight and durable when compared to other options for housing. To the knee unit must be strapped to the leg, so we wanted to make sure we had a breathable, comfortable material, and we found that neoprene was a good fit since it allows the user to keep the device on for a long period of time without sweat damaging the device. While using these materials and components, both devices are lightweight and small in footprint for their uses.
So phase three was the software phase, and this essentially made sure that our device functioned correctly at like a technological standpoint. And going through the requirements was the front end, back end, data storage, and Bluetooth transmission. So the front end allowed us or was designed to allow users to have like full touchscreen capabilities and access what they wanted to to perform on the device, and the back end would allow us to code the algorithm for our device, and the data storage would allow us to store data such as the amount of walking steps, and the Bluetooth transmission allowed us to transmit data from the knee unit to the heel unit back and forth. So the front end of the system contained options for how the user would select the device to perform. Here the user can calibrate the device, change walking modes, change the intensity, and on the right you can see that this is how the display would be set up on the touchscreen. The calibrate button would essentially calibrate the device as shown on figure 12. How the calibration works: the walking mode would set up the walking mode, and then the impulse intensity would be increased and decreased by the plus and minus buttons, which would work such as like an iPhone volume button, and the progress check button would essentially check the walking steps. So the backend is essentially responsible for the algorithm that performs the walking mode, the system calibration, and just until the intensity. It also tracks the progress and notifies the MCU of low battery. And on the right, you see the pseudocode for setting up the calibration. And essentially, the pseudocode sets up in such a way that the device will be able to sense the force that's being placed on the impulse is on the matrix electrode, and if a force is detected, then it'll be transmitted through a Bluetooth signal from the knee unit to the heel unit, and then the calibration will then be completed at the end. So the Bluetooth transmitter transmits data at 4 kilobytes per second, and this is optimal since that the pressure signal is less than 4 kilobytes per second, which is way less than for which is way less than the capacity that we have set with the Bluetooth signal, which would allow us to work without any issue. And the accuracy that we expect from the sensor is to the nearest 1 kilobyte. The storage is necessary for, oh, sorry. The storage would be necessary for storing data such as the amount of steps taken by the patient, and the accuracy that we would expect would be to the nearest 0.01 kilobyte. Here we have our software architecture. On the left side, you see the screen is the software architecture is an interconnected web of all our components in the device, and the screen is linked to most of the components necessary for our device to run, which is optimal since we want our user to select multiple components and be able to see and display multiple parts of it. On the right side, you can see that the Bluetooth receiver links the knee unit to the heel sensor, and I can take you through one of the chains right now with the knee unit sending data from the steps, and then the steps going all the way back to internal storage, back to the screen, which displays it for the end user. And the yellow lines, oh, well, you feel.
All right, so phase 4 essentially talks about the electronic design aspect of our device. So the first part of this phase was used to define and list all the major electrical components of our device. And this includes the main control units, sensors, screens, communication, etc. We made a trade-off table showing where we found all these electrical components, the specifications of each component, which was found on the part listing, and a brief description of each of the components. So this was done to make it easier to find the current draw and voltage requirements for each component, as well as to see if the electronic requirements of each device fit with each other and the device as a whole. It also helped us make sure we had the pieces that we needed to make sure our device functions properly. We didn't discuss the minor electrical components such as resistors and op amps because they're not essentially using power, they're only parts of the circuit. Next slide. So the electrical architecture of our design was the most important part for this phase. This section included the wiring diagrams of both our knee unit and heel unit, which was done using a software called FritzSync. These diagrams show where the components are going to be located in our device, as well as how many wires we would need to correctly wire the device. The block diagrams are for showing how data or power is going to be transferred from the main control unit and the rest of the electrical components in each part of our device. The benefit to using FritzSync to develop the wire diagrams was that we were able to implement our electrical components that we found from Adafruit, which is where we found most of our components from. We were able to download the part files for FritzSync and then basically transfer that over to the software, so it was easier to build our wiring diagrams. If one of our parts did not come with a fixing file, such as a dual coin cell holder, we just use an equivalent part from the part library as a substitute in the diagram. So for example, for our dual coin cell holder, instead of, since we didn't have a part file for it, we just used 2 single coin cell battery holders and combined them together. The way that the wires were correctly connected was we just basically checked the specification sheets for each component on Adafruit, and these essentially provided detailed diagrams of how the component would be correctly wired onto our Arduino. For the block diagrams, we started from the main control unit for each unit, which would be the Arduinos, and we used color-coded arrows to show if either power or data was being transferred to and from the MCU. And these diagrams give us a good idea of the connection between power and data in our integrated system. Next slide. So for the power consumption portion of our electric design, we basically calculated the amount of power that would be consumed by both the knee unit and heel unit of our device. This was done in order to make sure that the power supply of the batteries had enough energy to power every single electrical component that we had. How we did this was basically we listed out the current draw for each electrical component in the knee and heel units, and these values were taken from the trade-off table that was made in the notable electrical system section. We then listed the energy capacity of the battery for each unit in milliamp hours, and we divided this energy capacity by the total current draw of all the components in each unit to get a total battery lifetime. So the calculated battery lifetime for the knee unit was 12 hours and 6 minutes, while the battery lifetime for the heel unit was 30 hours and 20 minutes. And we decided these as reasonable numbers because usually rehab clinics are only open for 12 hours. So this made it so that they could run through a whole day without having to charge the device.
Phase 5 is the controls. For the system requirements, we got from a study that 0.7 meters per second is the average walking speed for a post-stroke patient. 1.4 meters per second is the average walking speed for a person with a normal gait. Both values from the study have a standard deviation of 0.1 meters per second, so percent overshoot is calculated as 7.14% of 1.4 meters per second. And 0.1 meters per second is also used as the steady state error. Also from the study, 0.85 seconds is the average drive time for a post-stroke patient and is used as the period of oscillation. Rise time is half a second, which is the average normal gait stride time. Using equations from class, the 4 right values were calculated, which are damping factor, natural frequency, settling time, and peak time. Next slide. Using the values mentioned in the previous slide, the leg speed while walking in meters per second versus time in seconds is graphed and plotted as shown in red. The graph reaches steady state toward the right-hand side of the graph. The first peak is the overshoot from steady state. Rise time is the time from 0 seconds to the first peak on the graph. Peak time is the time when the first peak is reached. The settling time is the time at which the oscillating speed reaches steady state. From visual analysis and comparing the 2 graphs above figure 17 and figure 18, the system is classified as second order and underdamped. Next slide. This is the control hierarchy flowchart. The orange line signifies the manual control flow, while the blue line symbolizes the automatic control flow. The most important component would be the operator of the device at the top of the flowchart. In this case, it would be the rehabilitation therapist. The operator would switch the device on or off and also be able to change the amount of stimulation to the patient's peroneal nerves to get the right gait behavior. This would all be done manually by the operator. However, the operating system of the device would have autonomous control over the other components of our system, including the piezo buzzer and the LED lights. The heel sensor would automatically control the main control unit to induce stimulation, and the accelerometer would automatically send the acceleration data for processing to the closed-loop tracking system. Next slide. The dynamic model chosen is speed control, since a person of normal gait is able to lift their foot with ease. Matching the speed in a stroke patient is important to rehabilitate gain properly. Considerations for this problem include what body movements are measurable with Arduino circuit components. The speed of the foot was chosen because an accelerometer can be used as a sensor to measure the acceleration of the foot. A simple calculation can be done to convert acceleration to speed, which the controller is capable of. Also, since there's already the heel component to the device, it will be easy to put the accelerometer in the housing of the heel component. We've deduced that the system for our device will be a closed-loop control system. The range of speed values in meters per second that the control system is designed for is 0 meters per second to 1.8 meters per second. The system takes in speed through the accelerometer, and then the controller converts the speed by using a simple derivative calculation. Then the stimulator is told to send or not send impulses to the musculoskeletal system to try and match the ideal output speed. This cycle repeats until the user stops using the device. Next slide. When a damping ratio of 0.64 as previously calculated and a natural frequency of 2 Hz also previously calculated are inputted into the equation for a g of s shown above, the graph is given as an output as displayed in red in figure 21. The system is second order because the system can exhibit a variety of responses to an input stimulus, and most systems are second order because of this. The second order response is underdamped because the damping factor is between 0 and 1. Next slide. All right, thank you, and any questions?